histological distribution to stand up to scrutiny. Yet in vivo, to our minds, it was a rubbery elastic system because its role is to avoid reaching a threshold of resistance at which the collagen might shear. It has to allow the tendon to move freely without transferring the movement to the surrounding structure. And it was around that time that computer-synthesized images came online. They made it possible to visualize structures as a system in perpetual motion with two rigid boundaries, a fixed external one and a fully mobile internal one. What we did was to introduce a cross-linking mesh-type architecture which included the microvacuoles on the armature. We then looked for the fractal distribution. The scientific approach and the graphic model pointed to the same apparent reality. There really was a sliding system with brilliant liquid lying between the vacuoles and an armature of collagen fibers. This confirmed what we had initially thought about the pulling and tugging going on between the vacuoles. Moreover, thanks to this discovery, we were able to confirm that not only the tendons were able to move independently from each other, entire organs could do likewise, so the system was common to the whole organism. It was then that we realized what we had discovered. This multi-microvacuolar collagenic absorbing system was to be found everywhere in the body. Stick view to be fully understood. So we began to look at the cutaneous and subcutaneous structures, which we thought we would find to be more stable in this mobile tisular environment. Initial scrutiny reveals basically two types of structure. Some are quite wide, with edges like knives and diaphanous surfaces. These surfaces are made of glycoproteinous derivatives. Others resemble longitudinal fibrils, which may be fine, long or short, swollen or cylindrical. At first sight, they look alike. But look closer, and you can see tremendous diversity. To use the jargon of physical mechanics, the arrangement can be termed a complex one, completely stable and in search of equilibrium. A system with tremendous capacity to resist and adapt to change. For physicists and doctors alike, there is no other such entity with so much cacophonous movement on the microscopic and macroscopic level. Movements involving the muscles, fluids, fibrils and cells. Here we are at the very heart of complexity. A Capernaum of collagen bathed in glycolicin with reservoirs of fatty microglobules storing energy, information, and matter. A communications network for exchanging energy, matter, and information between the component parts of the system to be conserved. Structures established by tensegrity are not stabilized by the resistance of each component part, like a column resisting gravity, but by a distribution and equilibrium between the mechanical stresses throughout the whole network. Such structures are therefore multidirectional, stable in all directions, and independent of gravity. These forces stabilize the structure through their equilibrium. But most importantly, all the forces are subjected to all the structural elements, with the result that the slightest increase in tension on any one of the elements is transmitted to all the others, even those the furthest away. Every request to morph mechanically in space. This ability of matter to organize itself spatially offers an infinite potential for movement. However, the collagen armature is only one player in this choreography.